All right, let's get into it. Today, we're cracking open the chemist's toolkit. We're going to explore the amazing fundamental tools they use to measure and understand a world that is completely invisible to us. So, think about a swimming pool for a second. It might just look like a big tub of water, but it's actually a super complex chemical soup. To keep it safe and clean, you have to add very precise amounts of different chemicals. And that's the tricky part. Because the water molecules, the chlorine ions, they're all impossibly tiny. So that brings up a really big question, right? How in the world do you count things like atoms and molecules when they're so small and there are so many of them? You can't just pick them up and put them on a scale one by one. You're going to need a special set of tools. Okay, let's do it. Let's crack open that toolkit and see exactly how chemists pull this off. Here's a thought experiment for you. Imagine you need to know how many people are in a giant football stadium, but you can't possibly count every single person. Well, if you knew the average weight of one person, you could just weigh the entire crowd and do a little division, right? Well, guess what? Chemists do something very, very similar. It all starts with knowing the weight of just one molecule. So the very first tool we're going to pull out is called formula mass, and it's basically how we weigh one single microscopic molecule. Put simply, the formula mass is just the total weight of all the atoms in a molecule added together. You find the weight of each atom, which is measured in these tiny, tiny units called atomic mass units, or AMU for short, and you just sum them up. And figuring it out is actually super straightforward. It's just 3 simple steps. First, you look at the chemical formula and see what atoms are in it. Second, you count how many of each atom you've got. And third, you just add up all their average masses, which you can find right on the periodic table. Let's see it in action. For something like chloroform, you've got 1 carbon, 1 hydrogen, and 3 chlorines. Add them all up, and boom, 119.37 AMU. Or for a more complex molecule like aspirin, you add up 9 carbons, 8 hydrogens, and 4 oxygens, and you land at a formula mass of 180.15 AMU. Simple as that. Okay, so this is cool, right? We can weigh a single molecule. But there's a catch. An atomic mass unit is an absurdly, ridiculously small unit. It's not something you can just measure on a scale in a lab. So this tool is helpful, but on its own, it's not very practical. We need some kind of bridge to connect this tiny, invisible world to our world, the one we can actually measure things in. And that brings us to our next tool. And honestly, this is the big one. It's called the mole. And the best way to think about it is like a chemist's dozen. It's the magical bridge we've been looking for. Get ready for this number. It's huge. It's called Avogadro's number. That's 602 sextillion. A number so unbelievably massive, it's almost impossible to wrap your head around. But this exact number, this is the key to everything. So a mole is really just a number that means a specific amount. Like how a dozen means 12 of something. A mole just means you have 6.022 times 10 to the 23rd of something. And here's the magic trick. If you have 1 mole of any element, its mass in grams, something we can easily weigh, is exactly the same number as its atomic mass in AMU. It is the perfect conversion factor. Just look at this. Each one of these piles, the zinc, the carbon, the sulfur, the copper, contains the exact same number of atoms, 1 mole's worth. But because the individual atoms all have different weights, 1 mole of each of these substances has a totally different mass. This is it. This is the breakthrough. We can now count atoms just by weighing them. And to really get your head around this scale, think about this. Just 18 grams of water, that's like a tiny sip. That's 1 mole of water. And that little bit of water contains over 600 sextillion individual H2O molecules. I mean, the numbers we're dealing with here are just absolutely staggering. Okay, so we've got our tools, we can weigh a molecule, and we have this amazing bridge called the mole. Now let's actually put them to work and see how they're used to measure the world all around us. Think about it. Most stuff in our daily lives isn't pure, right? It's all mixtures, like your morning coffee with sugar in it. How sweet that coffee is depends entirely on how much sugar you dissolved in it. In chemistry, that how much has a name, concentration. So, concentration is just the word for the amount of one substance, we call it the solute, that's dissolved in another substance, the solvent.
And the most common, most important unit for this in chemistry is molarity. And look at that, it uses our new favorite tool. It's simply the number of moles of a substance per liter of solution.
Now, molarity is the gold standard in the lab, but I guarantee you've seen other ways to measure concentration all over the place. On food labels, you'll see mass or volume percentages. And for really, really tiny amounts, like pollutants in the air, scientists use things like parts per million or even parts per billion. In fact, go grab a bottle of bleach from your house. The label probably tells you the concentration of the active ingredient as a mass percentage. This one here says it's 7.4% sodium hypochlorite by mass. All that means is that for every 100 grams of this liquid, 7.4 of those grams are the actual active ingredient. And in some fields, like medicine, getting the concentration exactly right isn't just important, it can literally be a matter of life and death. The standard saline solution they use in an IV drip has to have a super specific concentration of sodium chloride, 0.9%. That kind of precision is only possible because we have these incredible tools to measure the invisible. So whether you're talking about keeping a swimming pool clean, figuring out the right dose for a pain reliever like aspirin, or mixing a life-saving IV drip, it all comes back to this one fundamental toolkit: formula mass, the mole, and concentration. These are the concepts that let us measure, understand, and control the invisible world of atoms and molecules. So the next time you sweeten your coffee, check a product label, or even just take a sip of water, maybe you'll have a new appreciation for the immense, invisible, and incredibly fascinating world you're interacting with. Now that you have the tools, what will you see differently?